theorem we're going to prove is the Erdös-Stone theorem that you know from graph theory 1, which basically says that you have this Theorem number, which is the density of a graph that ensures that it contains Kr as a subgraph. So that is r minus 2 divided by r minus 1, half of that times n squared edges are the maximum that you can have on a graph of order n without Kr. If we have one more edge than this, then you will have a Kr subgraph. Right? So that's this Theorem number, T r minus 1 of n that's defined as the maximum number of edges you can have on n vertices without creating a Kr subgraph. So that's roughly half r minus 2, r minus 1, n squared. Okay, and the Erdös-Stone theorem tells us that if you have only a few more edges than this. Now, what is a few? You can tell me now. When I say few, what do I mean? I mean epsilon times the relevant reference parameter, right? If we have epsilon times n squared edges more, then we not only have a Kr, but we have a KRS, a complete bipartite graph with R classes, each of size S. And we're calling this epsilon, not epsilon, but gamma, so as to have epsilon free for the use of the regularity lemma in the proof of this. So plus gamma n squared for any gamma that we wish to choose. And the corollary, which I mentioned in our overview lecture on extreme graph theory, due to Erdős and Szymonovitz, 20 years later, says that you can do the same not just for Kr, but for any graph H, which you can force as a subgraph by how many edges? By chromatic number of H minus 2 divided by chromatic number of H minus 1 times n choose 2, the possible number of edges. This is n choose 2, roughly. Right? Okay, so that's the version of the corollary to the Erdős-Stone theorem that we use most often, but we'll now prove the Erdős-Stone theorem as it is stated there, just with KRS. In particular, you have lots of copies of Kr. Just choose one vertex from each of these classes. Then you have a complete graph on R vertices. And there's many, many ways of choosing them. Right? So containing even one copy of KRS implies that you're containing lots and lots and lots of copies of Kr. So just a few edges more than you need to force even one Kr give you millions of Krs hidden inside one KRS, which that additional number of edges forces. So the proof strategy is to use the fact that we have lots of edges on G and deduce from that that we have lots of edges on the regularity graph R for some D that we can choose. And since R has many edges, we can find on R, so how many edges do we want on R? More than 2 round number of edges. 2 round, not in n, but in the number of vertices that R has, which is k. So we want R to have enough edges that it contains a kr. And if it contains a kr, then Rs contains a krs, by definition. And then our lemma, the blow-up lemma, baby version, tells us that if krs lives in this Rs, which it does, it also lives in G. And that's the proof. Okay, so how should we choose our little d? We're allowed, in order to apply this blow-up lemma, we're allowed to choose d, the density. Should we choose that big or small? Should we go for high density or for low density? Well, we want R to have many edges, right? 2 round many edges, so that R contains a k little r. In order to give big R lots of edges, D has to be, yes, small, right? When D is small, then lots of pairs will have their density above this threshold D. So we're going to make D small to make life easier for ourselves to find kr in the regularity graph. Big R, but of course the blow-up lemma will make us pay for choosing little d small, and we'll have to see how small we have to use it, and then if we can pay the bill that the lemma will present us in return. So that's the idea. So let's look at what we need as input for the lemma. The big delta that we have to input, that was the bound on the maximum degree of h up to which we can embed an h found in Rs also in G, and that is going to be obviously the maximum degree of KRS, the graph we want to embed, RH, and the max degree of KRS, you work it out, whatever it is. That's going to be our big delta. Then little d is not at all obvious. It'll come out of calculations that we'll do later, and the solution is that d is going to be this little gamma, which sort of makes sense, right? If we choose gamma really small, which we're allowed to do, then the whole thing is going to be harder. We'll have to work harder in the proof, so we need a smaller d to give us more edges in the regularity graph R, and then we'll have to see whether we can afford that, whether these few more edges where gamma is small suffice to give us that. Okay, so as input for the blow-up lemma, we choose big delta to be the max degree of KRS. We choose little d as gamma, which is not obvious. And then the lemma will return some epsilon naught, right? And it also has this requirement that it only works for epsilon regular partitions whose class sizes are at least s divided by d to the delta. So the blow-up lemma will output epsilon naught, and it will output the L it requires for everything to work as a function of S that we can input, that we can still choose, and the D and the delta that we have already chosen. Right, so the output of the lemma is really this function. We can choose any S once D and big delta and epsilon are fixed. We can still choose little s, but we'll have to pay for choosing s big by the lemma requiring us to come up with an epsilon regular partition whose class sizes are big as well, namely at least L. Okay, so we can now use our little epsilon and input that in the regularity lemma here, right? If we choose little epsilon smaller than the epsilon naught that the blowup lemma sets us as a threshold, then we can also choose a lower bound little m, which is also not obvious what we should choose there. I can tell you now it's going to be 1 over gamma, but that will come out of the proof later. And then it will return, the regularity lemma will return an epsilon regular partition into classes of some common size L. And we want this common size L to be big enough to satisfy this. And what do we have at our disposal to still choose? How can we change L? Making G big. We're allowed to do that because Erdös-Stone only requires that something works for big enough G. Right? For every gamma, there exists a little n naught above which graphs of order n that have this many edges contain a KRS. So we're allowed to make G big, and the Erdös-Stone theorem will not mind that. And if we're allowed to make n, little n big, well, that's good news, because the number of partition sets that the regularity lemma returns is bounded by big M, and the big M depends only on the epsilon and the little m. Right? We fix little epsilon, we fix little m, then the regularity lemma comes back and says, here's big M. And no matter which graph you give me, it'll have an epsilon regular partition into, at most, big M sets. And we want these sets to be big. Well, no problem. We just make the graph big. And since there's only this many bounded number of classes, these classes are going to grow. They're all the same size. We can make them as big as we like. And this is as big as we like. Okay? So this little s, of course, is our s from the KRS. Okay, good. So what we still have to do is to show that R has enough edges to contain a K little r by Chourein's theorem. So let's try and show that we can't accommodate too many edges that are not going to contribute to blue edges in any other ways. What are the other ways? Well, edges on little v naught, edges from v naught to the outside world, edges in irregular pairs, edges in regular pairs of density smaller than d, and edges inside partition classes. So all these edges, let us show that there are not many such edges compared with the excess number of edges that we're allowed to sprinkle over our epsilon regular partition. Let me draw another picture. So how many edges can there be on useless edges? How many edges can there be on V0? Well, V0 has epsilon n vertices at most, so that choose two edges on V0 are possible, not too many. How many edges from V0 to the outside world? Well, epsilon n vertices can be linked each to any other vertex. So that's epsilon n vertices here to how many other vertices are there? Well, no more than n. So at most epsilon n squared, yes?
Why is it the blue expression 1/2 epsilon squared and n squared? Because epsilon n edges epsilon n.
Oh, here. Is that better? Thank you. Yeah. Right, so next, edges in irregular pairs. Irregular pairs. How many edges are there? Well, how many irregular pairs are there? No. Epsilon, I said epsilon k choose 2, but, well, let's call it epsilon k squared. Irregular pairs. When we have an irregular pair, how many edges are there between them? Well, all. So L squared possible edges like that. Now we want regular pairs of density less than D. Well, how many are there? Let's forget about regular pairs, just count any pairs, but make sure that we observe density is less than D. So once more, we have at most this many pairs. The number of regular pairs is roughly the same as the number of pairs in total number of pairs, because all but an epsilon portion of them are regular, so that's not going to be a big loss. At most this many pairs, and how many edges inside one pair? Well, D times L squared, right? So that's a small constant. And then we have edges inside classes plus K classes, K times L choose 2. I think I want half L squared there. Yeah, half L squared. Okay. So that's an upper bound on the number of useless edges. Now here's a riddle. For the blowup lemma to work, we only need a small portion of the edges, at least, say, 100th of all possible edges in those regular pairs. So what if we have half? Then we have more than 100th. We easily have more than at least half the number of edges. But something is wrong, because if we only have half the possible number of edges, then the Erdös-Stone statement is not going to be true. Right? Well, we don't even need to have a KR subgraph. Right? So if R minus 1 is 10, then we need 9/10 of all possible edges, even to get a KR. And we'll need more edges still to get a KRS. So we need 90% of the edges, which is fine because we have 99% of the edges in good places, but somehow the blowup lemma didn't seem to use them. If we have lots of edges in G, they can hide in few epsilon regular pairs and thereby only give few blue edges for R, where few is anything less than 2 run. So for example, if R minus 1 equals 10, right, then 2 run is 9 over 10. This is going to be 9 over 10. So we have more edges than 90% of the possible edges, but that means that we have edges in more than 90% of the possible pairs. Right? We can't accommodate 90% of all possible edges on the vertex head big V on n vertices. We can't accommodate 90% of the possible edges in fewer than 90% of the possible pairs. But we have more edges than that. We have these edges as well. Not only 90% of the possible edges, but those as well. And we need to show that the excess edges that we have cannot be tucked away in either irregular pairs or regular pairs of low density. And the way we're going to show that is by pointing out, not in irregular pairs, in irregular ways, that we have fewer than half of the excess edges, fewer than half gamma n squared edges in some irregular ways in G, namely in these ways. And that is why we chose this D to be gamma. Right, so you remember the Ramsey number of an integer, little r, and that was the least little n, such that when we two-color the edges of Kn, we can find a monochromatic Kr in it. Or in this version here, for every graph of order n, not necessarily a Kn, for every graph of order n, we can find Kr either as a subgraph of that graph or as a subgraph of the complement of that graph. Same vertex head, all the non-edges become edges. Right? So that's just two versions saying the same thing, stating the same thing. And the question is that if we say we don't want to embed Kr, but we just want to embed some sparser graph, H. is that going to make it easier? Right, so if H, for example, is a tree, rather than embedding a complete graph on R vertices, let's fix a particular tree, call it H, on R vertices, and might this n come down in size, the required size, such that for a smaller n, every graph of order that smaller n has the property that our tree H is a subgraph of it or of its complement. Does that make it easier to make H not complete? Yes, it should be easier. For example, if we replace KR with the graph on R vertices and no edges at all, we can definitely find it, even if n is R. So that's really, really easy. And we had a little lemma on Ramsey numbers in graph theory 1, embedding a tree against a KS subgraph, and that was already only quadratic in the order of these graphs. So, for example, if H is a tree on R vertices, then n equals R squared would be a nav. Okay, so the question then is how small exactly will this n be, and for which H can we get such a smaller bound? The Ramsey number is going to be linear, so that is really cool. So remember that Ramsey numbers for Kr, for the little r, are exponential in R. So there's somewhere between 2 to the half r and 2 to the 2r. That was the n needed so that every kn on any two coloring of the edges contains a monochromatic Kr. Right? So that was very much exponential, and now this comes down to linear for graphs of bounded degree, and here's the theorem. All right, for every big delta, there exists a constant c, that is going to be the slope of our linear function. There's a constant c, little c, such that the Ramsey number of any graph H of max degree at most delta, this Ramsey number is at most constant times its order, the order of H. The proof I'm going to show you is one of the earliest applications of the regularity lemma. So let me give you an overview of the idea. We want to show that any graph G that is big enough either contains H or the complement contains H. How can we be sure that H is contained in that graph? One way in our context here to ensure that is that we can apply the blowup lemma. Remember, H can be found in G if H can be found as a subgraph in some suitable RS. Okay, so let's set things up in such a way that H is a subgraph of some suitable RS, either for G or for its complement. So we need epsilon regular partitions of G and of the complement, and we need to look at those at the same time. Now, the definition of epsilon regularity is invariant under replacing a graph with its complement. So the epsilon regular partitions of G are precisely the same as those of G bar, complement of G. Right? So we can do both at once. And the way to do that is to choose an epsilon regular partition, or to find one, let the regularity lemma give us one of our graph G, and then consider the regularity graph for D equals 0. So all pairs count as dense. This regularity graph has a node for every partition class and an edge for every epsilon regular pair. How many partition classes are there? Little k mini. And all but epsilon k squared of those pairs are epsilon regular and therefore produce an edge, a blue edge as they were last time in our regularity graph R. Okay. Now comes the time to decide whether we want to find H in G or in the complement. And the obvious way to split this into these two cases is to say, okay, now this regularity graph has some edges that have density at most half and some that have density at least half. So we get subgraphs of this R. Subgraph induced by those blue edges where the density happens to be at least half, and all the others. Maybe the densities of exactly half are put in both subgraphs. Let's do that to remain symmetrical. Okay, so we have two subgraphs of R. One for the dense pairs and one for the not so dense pairs. And let's look at the dense pairs first. That's a certain subgraph of R. Let's blow it up to RS. Then RS, oh, it's gone. RS has all these classes. S vertices in each of them. Let's call it RS plus for the dense pairs. So this means density at least half. And which H can we embed there? Because if we can embed RH in here, the blowup lemma will tell us that we can find H also in G. This regularity graph for D equals 0 has some dense pairs and it has some not so dense pairs. That's a two-coloring of its edges, where the edges corresponding to pairs of density at least half are green, and those corresponding to densities at most half are red, so the edges corresponding to pairs of density exactly half are both red and green. Choose M to be the Ramsey number of this little r. Since K is at least, K is the order of R, is at least the Ramsey number of little r, we can find a KR in the red edges, or we can find a KR in the green edges. Suppose we've found a KR in the red edges of R. So that KR is a subgraph of R plus, and now we blow up this subgraph of R plus by replacing every node by S vertices. So we get these little R many classes, each of size S, inside RS. And there's lots of other classes as well. Now back to the question, which H can we embed in this graph here so that then those H can be also embedded in G? So that's a KRS. Which H embed in KRS? Well, all H whose chromatic number is at most the number of these classes, is at most R. Because when we embed this H here, we have an R coloring, right? These classes are all independent sets of vertices. When we have embedded H in this KRS, then we have, in fact, R-colored it. Conversely, if we have an R-chromatic graph H, we can embed it in this by mapping the color classes to these sets here, provided the sets are big enough. So let's make S big enough, easily big enough to do that. So for example, let's choose little s as the order of H. Remember, we are allowed to choose little s late in the blow-up lemma. Okay, so H embeds in this if the chromatic number of H is at most R. What does that have to do with max degree? Well, the chromatic number of any graph is at most its max degree plus 1. Right? So that was the easy, greedy algorithm. So as long as the max degree of H is plus 1, is at most R, we can embed H in here. Okay, so since the max degree of H is bounded in our case, it's at most big delta. The chromatic number is bounded, it's at most delta plus 1. And therefore, the R that we need here is bounded, namely by this chromatic number, delta plus 1. And so we can, by knowing this R now, we can then compute the Ramsey number of little r and input that at the start. By choosing little m here to be at least that big. Okay, so at this early stage, there is one thing to notice. I said we're fine because our max degree of H is bounded, but the only place where I seem to have used it is to say, okay, and therefore the chromatic number is also bounded, namely delta plus 1. And then everything went on autopilot from there. So might it be enough, could we strengthen the theorem to saying that for every H whose chromatic number is at most something, we have a linear Ramsey number? That would be a much, much better theorem. And the answer is no, because we need the boundedness of big delta, not only in this argument, but we'll also need it in order to apply the blow-up lemma. Remember here, the max degree had also had to be bounded. So we need it twice, and just bounding the chromatic number of H is not going to be good enough. Okay, thing we have to address is that the regularity graph R is not, in fact, going to be complete. I cheated a little bit by saying, well, since we use density 0, we're not making any requirements. Let's assume it's complete, and then its order is the Ramsey number of little r being delta plus 1. And since it's the Ramsey number, we can color the edges corresponding to whether the according to whether they correspond to dense pairs or not so dense pairs, and so on and so on. But in fact, R is not really complete. R is nearly complete. It may have some edges missing. The edges missing come from the irregular pairs. So we have to make a little adjustment, and let me do that now. Well, the number of edges is, and let me write this sort of slightly differently in an unusual way. Is this, right? Of course, it's k choose 2. It's half times k minus 1, but that's what you get here. Half times k squared minus k. And k squared minus k is k times k minus 1. Right, so that's correct. It's just an unusual way of writing it. And the reason I wrote it like this is that the Theorem number for m, t m minus 1 of k, the number of edges we can have on k vertices without getting a complete graph km. That is something rather similar. That is half k squared. And now we had m minus 2 divided by m minus 1. And let me write this like this. That's the Theorem number. And now these look rather similar. And in fact, which is bigger? Well, k is at least m, right? So this up there is bigger than that. We take less away, k is bigger than m, certainly bigger than m minus 1. We take less away up here from the 1 than we do down there. So there's a little margin, a little difference between the number of edges that a complete graph would have and the number of edges that will ensure a km. Any number of edges on k vertices bigger than this will give us a km. And the km is what we want to do Ramsey on. And the question is, do we get this many edges or one more? Well, we do, as long as the number of edges that are useless is smaller than this difference. Choose epsilon small enough to squeeze epsilon squared, k squared edges in here. Right? Epsilon k squared edges are the missing edges, the irregular pair edges. Well, we have more edges than we need, so choose epsilon so small that if we deduct those useless ones, we're still bigger than that. So here, the way we chose these parameters was that delta informed our choice of little m, right? Little m is the Ramsey number of delta plus 1, and this had this little m defined this gap, and the gap was all we needed to know in order to choose our epsilon here, but epsilon, of course, also has to be small enough for the blowup lemma to work. So the blowup lemma takes as input d delta, then d equals a half, and then the blowup lemma gives epsilon 0, epsilon naught, and we choose epsilon also smaller than this epsilon naught. Now we have found epsilon, and then the regularity lemma will return a big M. Will tell us that any graph has an epsilon regular partition into at most big M many classes. We want these classes L, the size of the classes L, to be big enough as input for the blowup lemma. We want the classes little l to be this big. Right? In order for the classes to become big, we need to know how many classes there are. Well, the regularity lemma will tell us big M many classes at most. And then we can make those big if G, the graph, is big in terms of this big M. Right? So we want G divided by this big M to be at least the little l that we need here. But that is easy because we can choose the constant little c from the theorem as 2 to the delta plus 1 times m. How are we allowed to use big M? I mean, big M comes out of the regularity lemma. How can we suddenly use that to define the constant for the theorem? Well, we can, because the theorem has as input only big delta. From big delta, everything else follows. From big delta, we can compute the Ramsey number of delta plus 1. So we know the little m. We can compute the epsilon, which has to fit in this gap here. That depends only on the little m. And it has to satisfy this. And this depends only on the big delta again. This is fixed. Right? So everything is fixed, even if unknown. But everything is fixed once we have chosen big delta. M, in particular, also will be output by the regularity lemma. It's some fixed value that depends only on little m and on epsilon, and both these we chose depending only on delta. So big M is some unknown quantity, which, however, is fixed once big delta is assumed to be fixed. And now we can choose this little constant c as 2 to the delta plus 1 times this m. And then G, order G divided by m, the size of the partition class is the size L, just works out to be exactly what we need for the blowup lemma.